All right, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1206. Let's make sure I can chat here. Okay, so let's get started. Last time we finished up an example from related rates. We spoke about maximum and minimum values. So we defined what's called the absolute max or the global max, and the absolute min and the global min. And these were the maximums across the entire domain or the entire interval that we're looking at versus things that are local, which is just in a single region. So you can be the biggest on the entire region like this guy is, or you can just be the biggest in your local neighborhoods like this guy is. Or you can be the smallest in the entire region like this guy over here is, the AM, or you can be the smallest in your local region like some of these LMs are, right? So that was the difference between absolute and local maximums and minimums. We spoke about that last time. So you're an absolute max if you're the biggest guy on the entire interval that you're considering. You're the absolute min if you're the smallest guy in the entire interval you're considering. And if you're just the biggest guy in some local neighborhood or the smallest guy in some local neighborhood, you are the local max and local min respectively. So we looked at that. We also looked at a very important theorem called the extreme value theorem, which pretty much tells us that we are guaranteed to be able to find absolute extrema in the case where the function is continuous on a closed interval. And we also saw a fun fact, Vermont's theorem, which basically says if you have a max or a min and the derivative exists at the point where you have a max or a min, then the derivative must be 0 at that point. The converse was not true. So just because your derivative is 0 doesn't mean you have a max or a min, so it doesn't go the other way. As well as it's possible to have a max or a min where the derivative does not exist. So because of those two things, we invented something called critical points, which pretty much told us the points that we want to look at where there's a possibility of there being maximums and minimums, because you can't know for sure. So we want to look at points where the derivative is 0 or undefined. And these are critical points. And these are pretty much the candidates for maximum and minimum points, as well as some other nice features that we'll care about. So as far as finding out where the local extrema are, right, local maximums and minimums, we already dealt with that actually. You do the first derivative test, which I already showed you. Or you could do the second derivative test, which we're not really going to look at. For absolute extrema, you do a method called the closed interval method, which is what I described here. So you find all the critical numbers in the interval that you care about. You compute the value of the function at the endpoints, and then you compare all these values. You find the biggest values from step 1 and step 2, and that will be your absolute max. Find the smallest values between step 1 and step 2, that'll be your absolute min. We did some examples of that, right? Finding critical points, where we pretty much went through and found the derivative, set it equal to 0 undefined, and found the x-coordinates that does that. Then we did finding an absolute extrema problem, which is a very important problem. I will test you on this problem. So we did the closed interval method. So we found the critical points, we tested them, we tested the endpoints, and then we compared all of them, and we looked at the biggest guy and the smallest guy, and those were our absolute max and min respectively. We also did a trig example. We then started the section where we want to talk about the mean value theorem. And before that, we had to describe something called Rolle's theorem, which is just a special case of the mean value theorem, as we're going to see in a few minutes. So there's a very, very important theorem in Calculus 1 called Rolle's theorem. And it's important because it helps us with the mean value theorem. And the mean value theorem is important because it helps us prove the fundamental theorem of calculus. So the mean value theorem is actually a super important theorem. So to talk about Rolle's theorem first, Rolle's theorem pretty much tells us that if our function is continuous on some interval and it's on a closed interval and it's differentiable on the open interval, and the endpoint, the outputs at the endpoints are the same, then there must be some value in between the endpoints where the derivative is equal to 0. And we actually prove that, right? And basically, this is an illustration of what's going on. Once your function is continuous and the derivative always exists, there has to be some point in the middle where your slope is 0. And given that these three things are fulfilled. So if you're continuous, the derivative exists, there must be some point in between A and B where the slope is 0. And it can be multiple points, as you can see here and here. It can be a single point, as you can see here, but there has to be such a point. And we actually proved that. And I think that's where we stopped. We didn't do anything after that. But you don't need to know the proof of Rolle's theorem, but you do need to know the statement. So I should probably say that. You do not need to know proof of Rolle's theorem. But you should know the statement. Of the theorem. Okay, so you should know what Rolle's theorem says. Says if our function is continuous on a closed interval, differentiable on the open interval, and the output at the endpoints are the same, then there must exist a point in between the endpoints where the derivative is 0. And we actually proved that using Fermat's theorem. And now what we want to do is move on to the next section, where we're going to talk about the mean value theorem. So let's actually do that. So now the theorem called the MVT, called the mean value theorem. So now we can actually state it. So let's actually just do that. So mean value theorem. So here's what it says. Again, assume f is defined on a closed interval and that f satisfies the following. So should I do 1 and 2 or A and B? 1, 2. Okay, 1, f is continuous on the closed interval. 2, f is differentiable on the open interval. And that's it, just those two things. So for Rolle's theorem, you needed 3 things. For mean value theorem, you needed 2 things. And then here's what the mean value theorem says. There exists a point C in AB such that the derivative at that point is equal to this expression, f of b minus f of a over b minus a. You'll notice that that is the same expression for the average rate of change, And so that's exactly what this is. This is the mean rate of change. Right? So basically it's saying that there's some point in the interval where the instantaneous rate of change has the same value as the mean rate of change. It will take on the mean value, hence the mean value theorem, right? Math people and naming things. We've been over that. Okay, so that's essentially what it says. There's some point in the interval where the instantaneous rate of change is equal to the average rate of change. Now, I do want you to appreciate some illustrations. That's the theorem. This covers Rolle's theorem as well. So if you look at this guy, do a couple of examples. So if we had our guy here versus here. So if your f of A actually equals f of B, that's A, that's B. Okay, then you'll notice that slope is 0, right? So that was a horizontal line. And here, slope is 0. So this would be our C, and this could be an example of a C, right? So notice here, your f of B minus f of A over B minus A would be 0 because they're actually the same. F of B equals f of A. And so, yeah, there are tons of points there, right? And we know this by Rolle's theorem, right? So this coincides with Rolle's theorem. Same thing here. If you look at f of B, if you look at f of B minus f of A over B minus A, again, you would get 0. And we're claiming that there's a point where it gives you 0. Now, this is exactly what Rolle's theorem tells us should happen. So you'll realize that these guys here coincides with Rolle's theorem. But the MVT is more general. So Rolle's theorem requires that our outputs at the endpoints are the same, but what if they're not? So here's another illustration. I'll do a couple more. So let's say my function looked like this. Right, so that's A. This is f of A. And that's B. This is f of B. So now your f of A and f of B are not the same. You'll realize what the average rate of change is. So if you look at this guy here, this is f of B. The slope here equals f of B minus f of A over B minus A, right? That's the average rate of change. But you'll notice that there is a point inside where if I were to draw the tangent line to the curve at that point, it's actually going to be the same slope, right? So the slope here is going to be f prime of some specific value, C. right? So there's a point C in the middle where the slope at that point, like here, is the same as the slope of the average rate of change. Like they'll both be parallel lines, right? That's supposed to look parallel. So what you'll notice between these two, it's the same value. Right, and similar, I can have this happening multiple times as well, just like in the last theorem. So you have that. A, B, F of A. So again, your F of A and your F of B are not the same. But I can find like the average rate of change, which is going to be just connecting the first and last points. But notice that I will be able to find coordinates where the tangent line, in fact, I'll be able to find multiple coordinates where the tangent line is parallel. Right, so this is a possible C here. This is a possible C here. Right, and so that's basically what this theorem says. As long as your function is continuous and differentiable on a closed interval, then there is a point where the instantaneous rate of change must be equal to the mean rate of change. It must be the same as it must take on the mean value, and that's called the mean value theorem. And of course, this kind of makes sense from if you sort of think about it physically. So imagine that you are driving. This reminds me of a YouTube video too, where never mind. Imagine that you're driving in a car. Just pretend you're moving at a constant speed, and you traveled 80 miles in 1 hour, right? And so the average rate of change is 80 miles per hour. So what this claims is, and you don't even have to be moving at constant speed. I traveled from point A to point B, which is 80 miles apart, and the average rate of change would be 80 miles per hour if I took an hour to cover that. So what the mean value theorem says is if on average you took 80 miles, on average it took you 1 hour to travel 80 miles, then there must be some point during that trip where you're traveling at exactly 80 miles an hour, right? You have to match the average rate of change. And if you think about it, that makes sense, because if you are never traveling at 80 miles per hour, that means you're always either above or below it. And if you're below 80 miles per hour, then you would never cover 80 miles in an hour. And if you're always above 80 miles per hour, then you would cover farther than 80 miles in an hour, right? So it has to be at some point where you have to be equal. So that kind of makes sense. So that's basically what the mean value theorem says. And it turns out that it's very intuitive, and it actually is very useful at the same time. So let's actually see why this is. And yeah, this is the same thing here, that your f prime of C is equal to f of B minus f of A over B minus A. And here your f prime of C is equal to f of B minus f of A over B minus A. So if you know the average rate of change, you also know that there must be a specific moment where the instantaneous rate of change is equal to the average rate of change, as long as your function is continuous and it's differentiable. Continuous on the closed interval specifically, and differentiable on the open interval. Once again, I'm going to prove this for you, but you don't need to know the proof, but you definitely need to know the statement. Let me mention that again. Yeah, so that's the mean value theorem. Okay. So now, how do we know this is true? Suppose we have f of x on AB that satisfy both assumptions in the MVT. Okay. Now what we're going to do is consider one of the most scary words in mathematics, because it usually means someone's going to pull something out of a hat and they're going to be like, well, look at this. And they're going to be like, okay. And then they're going to prove something with it to you. And you're going to be like, I see how that works out, but I don't know why you chose that thing in the first place. Yeah, that happens very commonly in mathematics. So yeah, consider this. We're going to define a new function. And this is how I'm going to define it. It's going to be f of x, but I'm going to subtract a certain quantity. I'm going to subtract this quantity. F of b minus f of a over b minus a times x minus a, right? So I want you to notice that this here is just a constant. In fact, it is it's the average rate of change, right? So now, since f is continuous and differentiable, so is g, since it is the sum of f and a linear function. So we know that if we add two continuous functions, you get a continuous functions, and a linear function is continuous. It's a polynomial. So if f is continuous, then f plus a polynomial is also continuous. Therefore, this continues. We also know that the derivative of a sum is the sum of the derivatives. So we know that f is differentiable, and we know that a line is differentiable, right? Y equals mx plus b, that's differentiable. So if I add them together, that is also differentiable. I would just take the derivative of each part. So it's continuous and differentiable. And here's something you can notice. Note, if I were to find g of a, right? So I'm going to go to g of a. So I'm going to plug this in. Wherever I see x, I'm going to plug in a. Now that is 0. So this whole thing goes to 0. And so you get that g of a is equal to f of a. Cool. All right. So that's one thing. Also, if I were to find g of b, this is f of b. And instead of x, I'm going to plug in b. That's going to cancel with that. So I'm going to have f of b minus f of b minus f of a. And that's just f of a. So notice that our g of b is equal to f of a, and our g of a is equal to f of a. So that's true. They're both the same because they're both equal to f of a. And this means g of x is 1, it's continuous on AB. 2, it's differentiable on AB. And 3, g of A equals g of B. Now, those 3 conditions are exactly the conditions we need for Rolle's theorem. So this means there exists a C in AB such that g prime of C equals 0. But what is g prime of C? This means that our 0 is equal to g prime of C, but g prime is just going to be, well, f prime minus, if you take the derivative of this function here, the derivative of a linear function is just the coefficient, right? So the coefficient of the leading term, right? So the derivative of mx plus b is, with respect to x, is going to be m. So this is just going to leave us with the coefficient here. Maybe I should put this over here so you can see it a little easier. So if you see this part right here, tells you that those guys are 0. So I can add this to both sides. And that gives you that f prime of C would be equal to f of B minus f of A over B minus A. So there must be a point where the derivative at that point is equal to the average rate of change. This has to happen, right? It has to happen because Rolle's theorem is true, and Rolle's theorem has to happen because of Fermat's theorem is true, and we already proved that yesterday. So that's the mean value theorem. And the statement is very important to know. And I will be asking questions about it, so you definitely want to actually know that. So that being said, let's actually do some examples. These are important. Find all values C that satisfy the conclusion of Rolle's theorem. for f of x equals x cubed minus 3x squared plus 2x plus 2 on the interval 0, 1. How do you know you can apply Rolle's theorem? And 2, it's actually going to be very similar. The mean value theorem for x cubed minus 2x squared minus 4x plus 8 on the interval minus 1 to 1. How do you know you can apply mean value? So these two problems, say this one is important. I would say this one is doubly important. I'm pretty much going to ask you about one of these problems for the mean value theorem for sure, like guaranteed. I might throw in a Rolle's theorem problem, but Rolle's theorem is kind of like the mean value theorem, except you have the equality and you want to show that the endpoints are the same. So you do need to remember these statements for the mean value theorem and for Rolle's theorem. And a problem I would ask would look something like this. Give you a second to like copy that or take a picture or something. Okay. So here is the first problem. A Okay, so find all values C that satisfy the conclusion of Rolle's theorem for this function on that interval. Okay. How do you know Rolle's theorem? We can apply Rolle's theorem. So let's actually answer that first. We know we can apply Rolle's theorem since f of x is, for one, f of x is continuous on 0, 1, because it's a polynomial. Also, we know that f of x is differentiable on the open interval 0, 1, again, because it's a polynomial. And since if I were to take f of 0, I would get 2. If I were to take f of 1, that'd be 1 minus 3 plus 2 plus 2. It's like 4 minus 3 is 1 plus 1. I would also get 2. So we have that f of 0 equals f of 1, right? So that's the requirement, that your f of a equals f of b, right? So these were the 3 requirements for Rolle's theorem. It's continuous on AB, the closed interval. It is differentiable on the open interval AB, and f of a equals f of b. Right? I don't know. Do I want to write this out? I think f of 0 equals 0 cubed minus 3 times 0 squared plus 2 times 0 plus 2 equals 2 equals okay. So you have those 3, and that's how we know we can use Rolle's theorem. Okay, so that's the first thing. So we know we can apply Rolle's theorem. So now the conclusion says there exists a C in AB such that f prime of C equals 0, right? So that's what Rolle's theorem, that's what we have to show. Okay. That's the conclusion. So let's actually show that that's true. So we have f prime of x is going to be equal to 3x squared minus 6x plus 2. So this means that f prime of c is going to be 3 times c squared minus 6c plus 2. So let's set f prime of c equals 0. This means that we get 3c squared minus 6c plus 2 equals 0. Does that factor? 3, 2, 6, 1. Doesn't factor. Okay, so jump into the quadratic formula. C is equal to minus b plus or minus the square root b squared minus 4 times a times c all over 2 times a. Let's see. 36 is 9 times 4. I can factor that out. It's going to be 9 minus 6. And 6 plus or minus 2 rad 3. That's 1 plus or minus rad 3 over 3. Now, this is let's say 1 over rad 3, so it's kind of obvious. So this guy here, 1 over rad 3, clearly it's less than 1, which means that if I were to subtract it from 1, I get a positive number. So notice that here. So note 1 minus 1 over rad 3 yeah, I could do it that way. C equals this is an element of this, right? It's less than 1 because I'm taking 1 minus something, but it's not less than 0 because I'm taking 1 and I'm subtracting something that's smaller than 1, and therefore I'm going to stay positive. But of course, if I took 1 plus 1 over rad 3, it's not in that interval. So I would reject this one. So I can conclude that C equals 1 minus 1 over rad 3 satisfies the conclusion. Okay. So this is one of those problems where if you don't know the statement of the theorem, it's going to be like, I don't know what to do. But if you know it, then each of these things are easy to check. You should be able to recognize that it's continuous, that it's differentiable pretty easily. The function is going to be something that you know how to differentiate. You should also be able to check that if I plug in the endpoints, I get the same values. And then all you have to do is find the derivative and show that where the derivative is 0, you can find a point that's inside the interval that you started with. And as long as that's true, you've satisfied Rolle's theorem, like the assumptions and the conclusion. So that's that. So there it is. The whole problem at a glance. So we can check that if it's continuous. We can check that it's differentiable. It's continuous on the closed interval, differentiable on the open interval. And f of a equals f of b, right? F of 0 equals f of 1. They both gave you the value 2. Then you found the derivative, and you realize that if it's 0, you can actually find a point in that interval that makes a derivative 0. And that's what Rolle's theorem says. There will exist a point in the interval such that the derivative is 0. That's pretty much it. And the equivalent problem for the mean value theorem is going to be very, very similar, except you don't need the third condition, which is f of a equals f of b. And the equation that you're going to solve is not the derivative equals 0, but the derivative equal to the average rate of change. It's pretty much the only difference. But the problems are very similar in that regard. It's much more common to ask like a mean value theorem problem on an exam though, because it's considered to be the more important theorem. In the sense that it's more general. Okay, so let's move on to the other one. Okay, so mentioned very important problem type. Find all values C such that the conclusion of the mean value theorem for this thing, C that satisfy the conclusion of the mean value theorem for this function on this interval. How do you know you can apply the mean value theorem? Okay, so let's actually deal with that first. That's easier. We know we can apply the MVT since f of x is continuous on -1 to 1 because it's a polynomial. It's also known that f of x is differentiable on the open interval for -1 to 1, again, because it's a polynomial. Polynomials are nice, they're continuous everywhere and differentiable everywhere. So they're definitely going to be continuous and differentiable on whatever interval you're concerned with. And that's all you need to know for the mean value theorem. So the conclusion of the MVT is there exists some C in -1 to 1 such that f prime of C is equal to f of 1 minus f of -1 over 1 minus a -1. So that's what we're going to figure out. So now f of 1 minus f of -1 over 1 minus -1. Where's our function? F of 1 cubed minus 2 times 1 squared minus 4 times 1 plus 8 minus f of -1 cubed minus 2 times -1 squared minus 4 times -1 plus 8 all over 2. All right, so let's see what we have here. We have 8 plus 1 is 9, and then you subtract 6. That's 3. Over here, we have 8 plus 4, that's 12, minus 3. So that's minus 6 over 2, which is minus 3. Also, now our f prime of x is going to be 3x squared minus 4x minus 4. Use that f prime of c is equal to 3c squared minus 4c minus 4. And we want 3c squared minus 4c minus 4 equals minus 3. So that would give us 3c squared minus 4c minus 1 equals 0. Does that factor? Via minus and a minus, which no, doesn't work. So no, it doesn't factor. So again, quadratic formula, c equals minus b plus or minus the square root b squared minus 4 times a times c all over 2a. I can factor out a 4 from the 16 and that guy over 6. So it's 4 plus or minus 2 rad 7 all over 6. 2/3 plus or minus radical 7 over 3. Now, radical 7 over 3, notice that rad 7 over 3, it's going to be between rad 9 over 3, which is 3, which is 1. Sorry. And it's going to be bigger than, say, rad 4 over 3, which is 2/3. So this is a number between 2/3 and 1. So, all right, so now, which means that c equals 2/3 minus rad 7 over 3 is going to be in this interval, right? And that's going to be close to 0. That's going to be somewhere between say 0 and minus 1/3. So that's definitely in there. Whereas but c equals 2/3 plus rad 7. It's not in here. Because 2/3 plus rad 7 over 3, that's going to be bigger than 2/3 plus 2/3, which is 4/3, which is already bigger than 1. So that's not going to work. Reject. So that's the C we want. And there we go. That's a fully worked out problem for the mean value theorem. So comes down to a matter of knowing the theorem, what it says, as well as just being able to verify that it works for some specific example. So that's what you're going to be asked to do. So it's a very useful theorem. Ultimately, it's very intuitive if you kind of think about some sort of physical example, such as just an object traveling at a certain speed and what that would actually mean. But yeah, in terms of Calc 1, this is what you're going to need to know how to do. I'm going to give you a function and I'm going to ask you, oh, verify the mean value theorem for blah. So show me that you can find a C that makes it the mean value theorem. It will illustrate that it's true. Yeah. So it comes down to you knowing what it says, what the assumptions have to be, and what the calculations need to say. The derivative needs to be the same as the average rate of change. So that's that. I'm thinking now if I want to. This pretty much ends the section. So I'm thinking it's kind of early to take a break, but at the same time, like I'm going to start something completely different. So it kind of feels weird to just continue. Let's see. There is some preliminary stuff that I do want to talk about, but is it stuff that I can talk about in half an hour? So now we already did 3.3. This is where we covered things like concavity inflections. Derivatives and the shapes of graphs, that kind of stuff. We actually did that prior. So we actually already did 3.3. I want to jump into 3.7, but I think I need to do some preliminary 3.5, but I need to do some preliminaries from 3.4. 3.5 is curve sketching. Yeah, I think I can do that. I think we can cover everything I need from 3.4, and like by the time we can get to our usual break. Okay, let's do that. what I want to talk about is asymptotes. So there are going to be two kinds of asymptotes that we're going to care about in this class, and I want to make sure that you actually know how to find them. So it's a word M. How about a definition? So an asymptote of a graph f of x is a curve that the graph of f approaches, I would say, like in the limit sense, as the x or y coordinate approaches plus or minus infinity. That's it. So examples. Y equals tan inverse is one example. So we know what that graph looks like. There's an asymptote here at pi over 2. There's an asymptote here, minus pi over 2. And the graph looks like this. Notice that as x approaches infinity, our y will approach pi over 2. So this is y approaches, let me rewrite it in a different way. Y approaches the curve y equals pi over 2, which is a horizontal line. Right? So as your x coordinate is going off to infinity, your graph is approaching a certain curve. What is that curve? It's the curve y equals pi over 2. That by definition is an asymptote. You can also go the other way. You can notice that as x approaches negative infinity, your y value will approach the curve y equals minus pi over 2, which is also a line. And as x goes to negative infinity, your graph is approaching this curve, and that's minus pi over 2, right? So it's just a curve your graph approaches as your x or y coordinate become infinite. You can have another one. So that's as your x becomes infinite. Let me give you an example as y becomes infinite. Say over x minus 1. So this curve would look like that, that. Okay. So notice that as your y approaches infinity, your x approaches the curve x equals 1. And as your y approaches minus infinity, your x also approaches the curve. X equals 1. And you can also see that as x approaches infinity, your y will approach the curve y equals 0. As your x approaches negative infinity, so these guys here are your asymptotes. The curve that you approach. So those are just examples of asymptotes. There are many kinds of asymptotes. We care about 2 types. Forget all the others. These are horizontal asymptotes which are referred to as HAs, and vertical asymptotes. Which are referred to as VAs. And these, as their name suggests, is just when your curve is a horizontal line or a vertical line. That's pretty much it. And yeah, we want to identify these guys. We want to identify when they would occur, what they are, what are their equations. So let's actually deal with one at a time. Okay, so how do you know where a horizontal asymptote will occur? Turns out that this one is pretty easy. Well, the one we're going to look at for vertical asymptotes is also pretty easy, but in general, vertical asymptotes are harder. But for horizontal asymptotes, it's actually not a big deal. You can actually find horizontal asymptotes by taking limits. So here it is. Suppose f of x is a function we can find the horizontal asymptotes of f if they exist by 1, compute the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x. And 2, if either of the above give a has to be finite, has to be a finite answer L. Then y equals L is a horizontal asymptote. Right, so y equals a constant is going to be a horizontal line, and that's how you would know what the constant is. You are going to take the limit, and it's going to tell you what that constant is. So you have this. You can have boom, 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 boom. This is the HA. And you can have a curve doing its thing. And you see that eventually to the right, you'll notice that if I call this L, you'll notice that the limit as x approaches infinity of our f of x equals L. There's our limit as x approaches negative infinity of f of x equals negative infinity. But this guy tells you y equals L is a horizontal asymptote. That's it. Yeah, that's pretty much it. I don't really need to tell you anything else. In some remarks here. In general, a function can cross its HA multiple times. So notice that this function here, I actually, come across the HA several times before actually settling there. That's okay. There's nothing wrong with crossing a horizontal asymptote. And you can always know if your function does by just setting your function equals to L, and you can solve for the x values at which it crosses it. We can find where it does by setting f of x equals L and solving for x. So that's one thing. Another thing I think is worth mentioning is that if f of x is a rational function, which we're going to be looking at a lot of the time, then it turns out that the limits will always give you the same value. If it's a rational function and it has an HA, then the limit as x approaches infinity of f of x will be equal to the limit as x approaches negative infinity of f of x equals, we actually know what this, is. It's the ratio of leading coefficients. So if you're looking at a linear function, which we will be doing pretty often, the limit as you go to infinity is actually going to be the same as you go to negative infinity. If you're not looking at a rational function, this is not necessarily true. We saw an example here with the arctangent. Limit as they're going to infinity is not the same as you go to negative infinity. But for rational functions, they will always be the same. Two, vertical asymptotes. All right, so suppose f of x is a function if if there is a if there are values a such that the limit as x approaches a from the right of f of x is infinite, or the limit as x approaches a from the left of f of x is infinite, then x equals a is a vertical asymptote. So it's pretty much when you reach a finite x value and your graph shoots up or shoots down, that gives you a vertical asymptote. Yeah, we already saw an example. You know, the y equals 1 over x. Right. So notice that the limit as x approaches 0 from the right of f of x equals infinity, and the limit as x approaches 0 from the left of f of x equals negative infinity. This tells you that x equals 0 is a vertical asymptote. And that is kind of it. Let's look at some remarks. First, while it is possible for a function to cross a vertical asymptote, it's not very likely in Calc 1. I'm not going to give you a function that does something crazy like that. If a function does cross a vertical asymptote, it's going to do it once, because if it does it more than once, it'll fail the vertical line test and it's not a function. But in Calc 1, we won't look at such functions. In section 3.5. So something like a piecewise function could do it. So you can have a function like it does this, shoots up, and then it does that, right? So here, if this is 5, then x equals 5 is a vertical asymptote, but clearly we cross it here, right? So it's possible to cross it, but it's not very likely. Here, if f of x is a rational function, it will not cross its vertical asymptotes. And the vertical asymptotes occur where occur at x values that make the denominator equals 0 when f is in put in reduced form. So anything that makes the denominator 0 when f is put in reduced form, that will give you a vertical asymptote. Why it's important that it has to be in reduced form? Because we have seen that if you have some factor in the denominator that makes the denominator 0, and then but you can reduce it and cancel it, what happens is you create a hole. You don't create an asymptote. So it has to be that you can't reduce and cancel the 0 in the denominator. And so your function literally has to avoid it. Technically, it has to avoid it even if you could cancel it, but it just creates a hole as opposed to like the function has to like not even go anywhere near it. So that's how you would actually calculate vertical asymptotes. I should give an example. Yeah, so y equals 1 over x. This is reduced. So we have this. Notice that x equals 0 makes denominator equals 0, and function is reduced. And f of x is reduced. So x equals 0 is a vertical asymptote. Versus, I can look at this function, f of x equals x squared minus 1 over x minus 1. And remember, we saw that this was actually just a straight line with a hole in it at x equals 1 with output 2. And so here, x equals 1 makes original denominator equals 0, but in reduced form, your f of x is just equal to x plus 1. Which does not have a denominator that x equals 1 makes 0. Right. Yeah, so that's the theory behind how to find them. And so mostly you're going to need to find them for rational functions. Rational functions, this is all you need to do. Reduce them, check after reducing what makes the denominator 0. That's going to be your vertical asymptote. That x equals that value is going to be your vertical asymptote. For horizontal asymptotes, you find these two limits. Limit as x approaches infinity of f of x and limit as x approaches negative infinity of f of x. And if either of them give you a finite value, then y equals that value is a horizontal asymptote. In all other cases, they're neither. in cases other than the above, we have neither HAs or VAs. All right, so yeah, pretty much right on time. It's almost 7:30. We will take a break here, and when we come back, we will do some curve sketching, which we're going to need to know how to find asymptotes for that. It's going to be one step in the process. So maybe I should. So for now, we're going to take a break. And then we'll do curve sketching when we get back. So let's do 10 minutes. Let's return around 7:40. And yeah, we'll see you guys then.
The show will start in 9 minutes. The show will start in 8 minutes. The show will start in 7 minutes. show will start in 6 minutes. The show will start in 5 minutes. The show will start in 4 minutes. The show will start in 3 minutes. The show will start in 2 minutes. The show will start in 1 minute. And now, on with the show.
Okay, welcome back. Hopefully you guys can hear me. You guys can hear me, right? Because I changed my headphones again. Okay, great. And I can hear you, so that's awesome. All right, so we're going to talk about curve sketching. Now, curve sketching, it's one of those problems where it's kind of weird. So a curve sketching problem is going to be the longest problem you're going to do in this class, for sure. Right, like doing a curve sketching problem from beginning to end, it's going to be time-wise and length-wise, it's going to be one of the longer problems that you do. I don't necessarily think it's difficult, but it's just going to take a long time to just get through everything. So just prepare for that. Second of all, we're literally going to sketch curves. And I know that in real life, no one's ever going to do that. Like you're just going to have a computer sketch curves for you. But the point of doing curve sketching, it's really to actually just test your knowledge of derivatives and what they mean for functions, and just, do you understand what are the implications of the things that we've been learning? And curve sketching is just a nice visual way to see that, oh yeah, they definitely understand. Like you can do this, you know what the second derivative is for, and you know what it would mean for a graph, and etc. So it's a very traditional Calc 1 topic, but the benefits of it is that it shows that you kind of know what it's going on, and it kind of has a visual representation of doing that. But like with related rates, we're going to do it in a way that hopefully is going to make it a little bit more manageable, more straightforward. I'm just going to give you a list of steps to do it. So if you go through these steps, you'll be able to do it. And usually in the statement of the problem, I would ask these steps anyway, so you kind of would know what you have to do, but I will just give you the steps. So curve sketching, let's actually jump into that. So it's pretty much what this is here. So in this section, there's nothing new that we need to learn. We're just going to put together a lot of things that we've been learning in chapter 3 so far, and we're going to put it towards sketching curves. Okay. So again, it's a 6-step process that we will be going through. And the idea is once you actually get through this process, you'll be able to sketch the curve at the end. Okay, so I'm going to give you a problem statement. And in fact, in this handout, this is kind of what the problem would look like. So I'm going to sort of ask you to do all this stuff. So this is like a typical problem type here. All right, so I'm going to ask you to find a bunch of stuff, and then at the end, sketch a curve with this given information. And usually I'm going to give you the curve. I'm also going to give you the first derivative and the second derivative, because in a test, I would normally have tested your ability to take derivatives already. In fact, I already tested that in test 1. So I'm not going to check on you that you know how to take a derivative. I'm actually going to give you the derivatives, and I just want to see, do you know what to do with them? Do you know what it means? How the behavior of the derivative affects things? Okay, so I'm going to give you a function. I'm going to ask, okay, find all this stuff and sketch the curve. And pretty much the things that you're going to have to find, even if I don't specifically state it, would be these things here that I mentioned in these 6 steps. Okay, so a curve sketching problem is just a problem where you go through these 6 steps. Okay, so I'm going to give you a function, and step 1 is you want to know what the domain of that function is, and it's not going to be some crazy function. It's going to be a regular function. Very usually, it's going to be a rational function. Pretty sure. Like I'm going to ask you a rational function. I'm going to tell you. Again, nothing up my sleeves. I'm telling you what I'm going to ask you. It's going to be a rational function. Okay, cool. So it's easy to know what the domain of a rational function is going to be. It's just denominator not equal 0. Cool. But of course, in general, it depends on what the function is doing. Okay. So that's the first thing. So that's step 1. Pretty easy. You just write down, oh, the domain is all x not equal to 1 or something like that. Right. So if I have like f of x is 1 over x, what you're going to do is, oh, the domain is negative infinity to 0, union 0 to infinity, not included. Okay, cool. That's the domain, not a big deal. Step 2 is you're going to find the intercepts. Again, not a big deal. Those are things that you did in algebra class, right? So to find the x-intercept, you set y equals 0, solve for x. To find the y-intercept, you set x equals 0, solve for y. Okay, so that's fine. The third thing you're going to do is what we just learned. You're going to find the horizontal and vertical asymptotes. And I already discussed how to do that, but I do some notes where I reminded you here of, right, so there are some notes here where I remind you how to do that. Oh, you find the horizontal asymptotes, you do these 2 limits. To find the vertical asymptote, it's either this or this that has to happen, and you just want to make sure that the denominator is 0 and the numerator is not 0 for the same time. Okay, cool. So, and that's basically just saying, okay, once you reduce it, you still have it as 0 in the denominator. So that's the third thing you're going to do. You're going to find the asymptotes by doing those calculations I mentioned earlier. And the fourth thing you're going to do is you're going to find the intervals of increase and decrease and the locations of local maximums and minimums. And how are you going to do that? Well, the first derivative test, of course. So you're going to find all that information. So you're going to tell me what interval the function is increasing on, decreasing on. Are there any maximum points? What are their coordinates? Are there any minimum points? What are their coordinates? That's going to be the 4th step. You're going to have to go through the first derivative test to do this. The 5th thing you're going to do is you're going to find the intervals of concavity, which means you're going to tell me it's concave up on this interval, concave down on this interval, etc. And then potentially there might be inflection points. You're going to tell me what these are. You're going to tell me, oh, it has an inflection point here, right? Tell me the coordinates of the inflection points. So that's the 5th thing. Now, with all those things, you can do step 6, which is to actually finally draw the picture. Right, so you're going to go through these calculations, you're going to calculate all these things, and then you're going to use that to draw a picture. And the picture must satisfy everything that you found before. It must have the right concavity at the right times. It must have the right max and min points, if there are any. It must have the right asymptotes, if there are any. It must have the right intercepts, if there are any. It must show that you have the proper domain, etc. Right, everything has to agree. And that's kind of it. So nothing here I think should be weird or out of the ordinary. It's just that to actually write this all down is going to be a long process. Just accept it. It's just the nature of the beast. That's how it is. So of course here I also mentioned some rookie mistakes. Just not being great at your algebra, not using the right derivative for the right thing, which happens occasionally. Another rookie mistake that I've seen happen sometimes is that students they don't obey their previous calculations. So they'll do a calculation there and they'll say, oh, there's 1 x-intercept. And then they'll draw a picture where there are 2 x-intercepts. I'm like, you just said there was 1. Why does your picture have 2? Right, so things like that. Just like not being consistent is just like a mistake that I see from time to time. So if you're okay with your algebra, you know how to do the calculus stuff, and you're just consistent, you're going to get this problem correct. But that being said, just know it's just going to take forever. I'm just going to be real. So there are a bunch of examples here. where just to kind of ease you into it, I give you some very simple examples here. Some are polynomials and stuff like that, which I'm not really going to ask you anything like that. But you could use these techniques on virtually anything, any function that I would expect you to be able to graph in Calc 1. However, on a test, your problem is going to look mostly like this here. Right? So I gave you 3 examples here. I'll go through 2, maybe 3 of them, I don't know. But yeah, this is kind of what you should expect it's going to look like. Now, of course, on Gradescope, the formatting might look different. I might ask you to do each of these in a different cell or whatever, but I'm going to ask you the same things, right? So it's going to say, okay, consider the given function f of x. The formulas for f prime and f double prime are given. They need not be verified. So I don't want you to waste time finding derivatives. I'm going to give you the derivatives. You don't have to waste time calculating them. Don't verify that I gave you the right derivatives. Just assume I gave you the right derivatives and move on. So then I'm going to ask you, so now I'm right here. I'm going to ask you specifically, find all the intercepts, asymptotes, relative extrema, intervals of increasing and decreasing, intervals of concavity, and inflection points if they exist, and use the information to sketch the graph. Indicate on your graph all the features above, right? So that's basically going to be it. So you're going to find all this stuff, and then you're going to graph it, and then you're going to show me on the graph where all of this stuff came into play, right? And that's basically it. And yeah, that's kind of it. So we're going to do that now. So let me copy this here. The problem on your test 2 and final will be similar. I don't know how many examples I want to do, but I'm just going to copy pictures of all 3 parts, just in case the mood strikes. Doing it on my other screen. quite a few of these. All right. So let's do that. Let's go into the examples. Okay, so here's the first one. And the problems, like I said, is going to be all of this stuff. But we're going to go through those 6 steps. So you're going to see me going through the 6 steps, and it's always going to be the same thing, right? Just like with related rates. So you guys can write this down if you want, but I should be reminding you all the time. Okay, let's get into it. So usually the problem is going to be, oh, find the domain, find the intercepts, find the asymptotes, find the intervals of increasing, decreasing, find the intervals of a concavity, find relative extrema, find inflection points. Either way, you're always going to want to start with the same thing, pretty much in the same order, I think. I would do it in the same order. Where you find the asymptotes don't really matter much, but might as well just, it's easy to just knock them out. So just do it. Yeah, so one, what we're going to do is you're going to find the domain. And at this point, I'm not going to check that you know how to find the domain. Just stating the domain is going to be good enough. You're going to realize here, x squared minus 4, x cannot be plus or minus 2. So you're pretty much going to just state that. That's it. That's your domain. Move on. Like I'm going to give you like 1 point for the domain. So it's something I just expect you to eyeball and know, right? So yeah, that should be obvious. Now moving on, the next thing we want to do is intercepts. Now remember, for the intercepts, your x-intercept, you're going to set y equals 0, solve for x. So that means your x squared over x squared minus 4 equals 0. This means that your x squared equals 0. This means that your x equals 0. That's your x-intercept. For y-intercept, you're going to set x equals 0. Solve for y. So that's going to be y is equal to 0 squared over 0 squared minus 4, which is 0. So y equals 0 is going to be your y-intercept. Cool. So far, I don't think anything should be out of the ordinary. Right? So the domain and the intercepts should be okay. 3, now this is slightly different, so you might have questions here, and that's okay. Just let me know. Asymptotes. Do them one at a time. I would start with the horizontal. Doesn't matter which one you start with, but force of habit, I always start with the horizontal. So you're going to find the limit as x approaches infinity of f of x. And you're going to find the limit as x approaches negative infinity of f of x. Now this is going to be, if you look at that, x squared divided by x squared minus 4. Should realize that this is 1. And this is, of course, also going to be 1. So this means y equals 1 is a horizontal asymptote. And that's it, right? So we know that this is 1 by the ratio of leading coefficients trick that we learned in limits forever ago, which is like a week ago or something. Yeah. So that's your horizontal asymptote. And you are going to do the same for, well, not the same. You then move on to the vertical asymptote. And this is just going to be where your x is equal to 2 or minus 2. because this guy, x squared over x squared minus 4, that's reduced because you can't, you factor the denominator into x minus 2 times x plus 2. You can't cancel anything from the top. So whatever made the denominator 0 is going to be your vertical asymptotes right away. These guys make denominator 0. And are not canceled in reduced form. So that'll be your asymptotes. Any questions on the asymptotes part? So that's something that's relatively new. Not relatively new, like we did this today. Yeah, that's the asymptotes part. Now we move on to step 4. Now here's where we're going to find increasing, decreasing, maximums, minimums, right? And then for that, obviously, we're going to need this guy is what is important. We're going to do the first derivative test. So what we're immediately going to do is find the critical points. Notice that x equals 0 and x equals plus or minus 2 are the critical points, right? Because here is where your f prime equals 0, and here is where your f prime is undefined. Okay, so that's going to be that. And so now what you're going to do, remember the first derivative test, how that works. Once you find the critical points, you're going to plot it on a number line. So we have 0, we have minus 2, we have plus 2. We're going to pick random numbers in between, say minus 3, minus 1, plus 1, 3. You're going to plug them into the first derivative. So the first derivative, notice that the denominator here is always positive. So you really only need to check the numerator. So here we're always going to have a positive in the denominator whenever the denominator is not 0. So only need to check the numerator. Now minus 8x, if x is minus 3, that's a negative. If x is minus 1, no, that's a positive. And if x is 1, that's a negative. If x is 3, that's a negative as well. So here, this is positive, positive, negative, negative. So this means we're increasing, increasing, decreasing, decreasing. Okay. So now this guy is the only candidate for a max, right? So that's going to be a maximum point. And in fact, we can know the coordinate 0, 0, where remember for a coordinate, it's the original function that you're using, not the derivative. Yeah, so we're increasing to the left of 0, decreasing after 0. 0 is where we hit the maximum point, and 0 is in the domain. So this point actually exists on your graph. So that's your maximum. There are no minimums, right? So at this point, you now have enough information to deal with step 4. So we want to find where is it increasing? Where is it decreasing? Where are the maximums? Where are the minimums? So as you can read here, we're increasing from negative infinity to negative 2, as well as negative 2 to 0. We're decreasing from 0 to 2, as well as from 2 to infinity. Maximum occurs at 0, 0. Minimum, there are none. I want you to, and so this is the answer for this part. I want you to notice that these guys are intervals. Well, this guy is a coordinate. But yeah, that's that section. That's the first derivative test. So you're going to set the derivative equal to 0 or undefined. You're going to draw this number line. You're going to test points in between. You're going to see if it's positive or negative. You don't care about the actual value. So notice here, I never computed the exact numbers. I just realized, well, the denominator is always positive because it's a square. So then I just look at that, the sign for the numerator. Whenever x is positive, minus 8 times x is going to be negative. So on the right side, it's negative all the time. On the left side, it's positive all the time. Like the actual values you don't care about. Because the actual values will change a bit from person to person depending on the number you pick anyway. So the important thing is in between the critical points, the value is always going to be either positive or negative. It's not going to change on you. So you don't even really care about the actual value. Right, so, and that's the first derivative test in all its glory. So now you move on to the next phase, which is step 5. Here you're going to find concavity. So we're going to figure out where it's concave up, where it's concave down, where are there inflections? Are there inflections, right? We don't know, right? We have to figure that out. But that being said, in this phase, we will use the second derivative, of course. And you're going to want to know where is that 0 or undefined. So we're going to need the critical points. Here, there are x equals plus or minus 2. And we know that because the numerator is never 0, it's 3x squared plus 4. That's always at least 4, and then you multiply that by 8. So the numerator is always positive. So the only thing that creates a critical point is where the derivative is undefined. So this is where f of x, f double prime is undefined. Again, we're going to do a number line. This time we're going to plug into the second derivative. And we are going to have minus 2 and positive 2. We're going to pick random numbers in between, say minus 3, 0, 3. Technically, any number you want can work, but of course, just pick a nice number, right? So technically, instead of 3, I could have picked 17.298. Why would I do that? It's not necessary. Just pick any number. 3 is a nice round number. It's the smallest round number, whole number that's greater than 2. Pick that. Right? And then you do the signs again. So this time the numerator is always positive because notice that the numerator is the square plus a positive number. So this is always going to be positive. So now it's the denominator that I care about. Now, if x equals minus 3, x squared is 9 minus 4, that's positive. So it's positive here. Similarly, if x equals plus 3, you would get a positive. In between that, like x equals 0, 0 squared minus 4 is negative. You cube that, you get a negative. So that's negative. So this is a positive, positive. This is a negative. Now, what does that mean in the second derivative? Does it mean we're moving up or down? It means neither, right? Remember, second derivative tells you about concavity. It does not tell you about increasing or decreasing. This tells you we're concave up, like a cup, down like a frown, up like a cup. So here we switch from concave up to concave down. So this should be an inflection, right? Are those inflections? See if you guys go. Following.
Yes.
Okay, so the answer is no, but why is it no? Is what I want to. But yeah, this is it would be a very common mistake for someone to just assume that that's an inflection point. Why is it not an inflection point? So you would ask yourself, because you know what makes an inflection point. It's when you switch from concave up to concave down, right? So you see this and you're like, whoa, I went from concave up to concave down. That should be an inflection point, right? And the answer is no. Do you see why it's no?
Maybe there's an asymptote.
Is there? So if you go back up to the domain, look at that. -2 and 2 are not in the domain. Yes, it is an asymptote. In fact, it's a vertical asymptote. And so that's the issue, right? So that's why the domain is important, right? So the domain, what can happen sometimes is that your graph will do things that look like a max or a min or an inflection point, but the point is actually not even on the graph. There's no point there. So it's like you can't be any of those things. So that's why looking at the domain is important. So basically it's no because -2 and 2 are not in the domain. They can't be inflection points. They're not even points. There is no point at x equals 2. At x equals 2 and -2, you divide by 0. So be careful of that. That's a common mistake. So you want to pay attention to like all the parts and just don't forget anything that you did before. So we don't have any inflection points, but we do know about concavity. So what we can figure out here is where we're concave up, where we're concave down. Are there any inflection points? So where we concave up, you'll notice that we're concave up on -∞ to -2. We're also concave up on 2 to infinity. Where are we concave down? Between -2 and 2. Where are the inflection points? Well, we have none. The only possible candidates for inflection was -2 and 2. However, it's not in the graph. Again, to just remind you, these guys are, what was that? These guys are intervals. Well, this guy would be a coordinate, but there's none, right? And that's that. So now we reach to step 6, which is to graph. Okay. So this is all the work we've done to get to this point, right? Let's see, it's very long to actually draw it out. At any given time, we're not doing anything completely crazy, especially since we're not even having to do the derivatives. I'm going to give you the derivatives. So it's really just a bunch of algebra. The calculus just comes in when, do you know what a positive number here means, right? So in this case, it means concave up, while in this case, it means increasing, right? So that's where your calculus knowledge is coming in. You don't have to do any computations with the calculus. But yeah, now we want to draw the graph. Now the graph itself has some steps to it. At least that's how I would do it to make sure I'm not missing anything. So when it comes to the graph, here is kind of how I would do it. How to construct graph. The first thing I would do is I would put in all the important coordinates. So these are like the intercepts, max, min, inflections, right? So anything that was a coordinate that you found, I would put those in. The second thing I would put in are the asymptotes. So you're going to put in your horizontal asymptotes, your HA and VA. The third thing I would put in would be the intervals. So intervals of increasing, decreasing, intervals of concavity. Fourth thing, right now I would start to put in the curve. Following the above features may require some testing, which I'm going to show you what the testing would look like. Test to kind of know that you're drawing the graph correctly. Okay, so what would that mean? So what do we have? We have intercepts. I believe that was just the origin. So you go back. Okay, my origin, right, x equals 0, y equals 0 were the x and y intercepts. So that's going to put that in. So I know that that's an intercept. Okay, cool. What else do I know? I know what are, oh, the origin is also a maximum. So that intercept is also, just going to label it right here, max. Do we have any inflection points? No. So I just finished the first thing. I put in all the coordinates I have. We had intercepts, which was the origin. We also had a maximum point, which is also the origin. We did not have any minimum points. We did not have any inflection points. So all the points, I just filled them in. Next, asymptotes. Need asymptotes. So what were the asymptotes? So you go back here. Oh, the horizontal asymptote was y equals 1. And the vertical asymptotes were x equals -2 and x equals +2. So I'm just going to go here. I'm going to put those in. So those are broken lines. This is y equals 1. That's the horizontal asymptote. Then I'm going to put in vertical asymptote. So this is x equals 2. So vertical asymptote. X equals -2. So vertical asymptote. So I put in the asymptotes, right? So these guys are broken lines. They're not actually on the graph, but they are curves that the graph has to maneuver around. Okay. Now, that's the second thing that we just did. Now we're going to put in the intervals of increase and decrease and the intervals of concavity. Now here's how I would do the intervals. I would actually draw them below the graph in a little diagram. So let me show you what that would look like. So increasing, I know I'm increasing between -infinity and -2, and then -2 to 0. So increasing, this is -2, this is 2. I know from here and back, I am increasing. And then from here to here, I am increasing. Right, so I kind of lined that up with where I know I'm increasing. So from -2 backwards, and between -2 and 0, I'm increasing. I am decreasing between 0 and 2, and I am decreasing after that. And so that's how I'm filling in my intervals. Similarly, I look at concavity. I'm concave up from -infinity to -2, and from 2 to infinity, and I'm concave down in between. So I'll put that in. Here I'm concave up. Here I'm concave up. And all the way in between, I am concave down. I just put in the intervals. So now we're ready to actually plot the graph. Okay, so here's how we're going to do it. So now we have to know where we are, right? So on one hand, sometimes you plot coordinates, and that's good enough. Like we have one coordinate plotted already. So I kind of know where I should be in this region. So I kind of know what I have to be doing here. Notice that on this side here, right? When I'm in this region here, notice I'm increasing and concave down. Now remember what that means. Concave down like a frown. So I'm increasing, but I shape like a frowny face. So the graph here is going to look like this. Right? So I'm increasing, but I look like a frowny face. Let me do that a little bit more bubbly. So notice I'm not touching the vertical asymptote because I would divide by 0 if I did. But in this here, I'm increasing. I'm going up as I go from left to right, and I look like a frowny face while doing that. This will show me that you know, oh, I know what concave down means, and I know what increasing means. So if you drew something that's not going up as you go from left to right, and if you drew something that does not curve like a smiley face, a frowny face, I'm going to assume like this person doesn't know about what concavity means, right? Because he would not have drawn it that way. Similarly, and this kind of goes off weird. Maybe I should. If I'm looking in this region over here, where I want to draw in next, notice that I am in the region where I'm decreasing and concave down. So, I'm going to look like this. And that should look more symmetric. It's not going to be perfect. I don't expect you to be perfect either when drawing this stuff. But yeah, so that's what the middle part of the graph looks like. Notice that it fits everything that I found before. It passes through the origin, which is an intercept. The origin is actually a local maximum. If you zoom in around the origin, the origin is the highest point on the graph. It is concave down in the entire region, shaped face, and it's increasing between -2 and 0. It's decreasing between 0 and 2, which it's supposed to be doing. Okay, so now we want to do this, the rest of the regions, right? So what we can do now is we don't actually have a coordinate anywhere over here to actually know where we are. So there are a couple things you can do here. One is you can actually just, by trial and error, just kind of ask yourself, can I be here, here, or here, right? Just split up all the regions in terms of the asymptotes and above and below the x-axis, and kind of ask yourself, which one is possible, right? So would it be possible for me to be down here, you might ask, right? And the answer is no. And why is it no? Because in this region, you're supposed to be decreasing, right? And concave up. Now that is actually a problem. You see, if I'm decreasing, I have to be doing this, right? Now, if I'm decreasing, concave up, my graph would have to look like that. I'd have to be going down as I go from left to right, concave up like a cup. I have to be going down as I go from left to right. Now that's going to cause an issue because that would cause an intercept, right? And I remember I only have one intercept. It's at the origin, which means that cannot be the case. So it means I'm not down there. All right. What about here in the red? Could I be right here? Similarly, I have to be decreasing concave up. Now, this is also an issue because one, I can't continue here because that would create an intercept. But I also can't go here and do that to get to the horizontal asymptote. The reason why is I would actually create a minimum point by doing that. This would be a minimum point. I would also have to be now concave down like a frown. So that's not possible, right? Because it doesn't agree with all the other things I found. So I can't be in the middle either. The only possible place that I could be is above, in which case, if I'm decreasing and concave up, I would have to look like this. Notice that I'm decreasing concave up the whole time. And it fits everything. It's decreasing, it's concave up. I didn't create any new extrema. I didn't create a maximum or a minimum point. I didn't create a new x-intercept. That's how the graph has to look. There's no other choice. Similarly, you can do here. I can't be down here because I would have to be increasing. It would create an x-intercept. I also can't be here because I'd have to increase, and I'd either create an x-intercept or I'd have to come back to fit this horizontal asymptote, in which case I would create a minimum point. So again, I must be up here. And so the graph would have to look like this. Right? And that is the graph, right? I know that I never crossed the horizontal asymptote. So maybe I should label these 1, 2, 3, 4, 5, 6. Note, we cannot be in regions 3 or 6 since we'd create an x-intercept. We cannot be in regions 2 or 5 since we'd create 2 or 5 since we'd create an x-intercept and or minimum and or a concave down curve to fit the HA. Right, so there are a bunch of reasons why we couldn't be in regions 2, 3, 5, or 6, right, which is what I mentioned. And so we have to be there. Also, in addition, notice that I never had to figure this out before. But you might be wondering, could I cross the horizontal asymptote? And the answer is no, because you'd have to come back up to meet it, which would create a minimum point. So you know that doesn't happen either. But also we can know we never touch the HA because f of x equals 1 has no solution. How do I know? Well, my f of x is x squared over x squared minus 4. If that equals 1, this would mean that my x squared equals x squared minus 4. This would mean that 0 equals minus 4, which is absurd. So I know I never cross it there. And also, crossing the HA would create a minimum. Because remember, the horizontal asymptote is what we approach as we're going to infinity or negative infinity. So if I cross it, I'll eventually have to come back to level off. Once you go back, you create a minimum, which I know there is no minimum. So at the end of the day, that's the graph, and you can kind of look through, make sure that you're fulfilling all the features that you found above. Everything on your picture should agree with the calculations that you did above. And that's how you know you're doing it right. So once you draw a part of your picture and you're like, wait, that doesn't make any sense because I just made an x-intercept and I'm not supposed to have one here. So just pay attention to that stuff and you'll be fine, I think. I mean, other than that, are there any questions on curve sketching, anything that I did? So the entire, or you can't even see the entire problem. Yeah, like that's the whole problem. Like it's long, and like I said, that's to be expected. It's one of the longest. This problem type is the longest problem type you'll be doing. There are a couple things that are pretty long, like related rates is somewhat of a long process. Optimization, which we'll be covering soon, is kind of a long process. But curve sketching, I think, is the longest one. But that being said, what you're doing in each section is easier than almost anything else. So it's just long, but you have to, it's straightforward once you know the steps and you know how to go through them. What we could do is we could do this one just to kind of run through another example. I don't know, maybe I could do the other two. Okay, so in terms of timing, I would say you should be able to do one of these in about 15-ish minutes. So maybe I should write that somewhere. Curve sketching problems are long, but you should aim to be able to do them in roughly 15 minutes. You don't want to spend longer than that on a curve sketching problem because it means you're probably going to run out of time on something else. So when you're practicing for the test and you're practicing some of the practice problems, just try to get through a problem within like 15-ish minutes or so. Okay, that being said, let's try to do another example. We have about 25 minutes. Maybe we can try to get through 2. I don't know. But yeah, let's actually do it. So here's another example, and I'm just going to kind of go through it, and we'll see how we do. So 1, we're going to check the domain. Domain is all real numbers here. 2, you're going to do the intercepts. Your x-intercept is going to be x equals 0. Your y-intercept is going to be y equals 0. 3, going to look at asymptotes. Let's look at horizontal. You're going to find the limit as x approaches infinity of f of x, which is going to be 0 because it's bottom heavy. This is also going to be the same as the limit as x approaches negative infinity of f of x. This means that y equals 0 is a horizontal asymptote. You can look at vertical asymptotes. This will occur where the denominator is 0. It's never 0. There are none. 4, we can do increasing, decreasing, maximum, minimum. In which case, we're going to look at the first derivative. So we're going to find the critical points. This is going to be x equals plus or minus 1, because that makes it 0. So I'm going to, in the derivative, put in plus or minus 1. I'm going to pick some random values in between. I'm going to plug into the first derivative. Now, the denominator is always positive. So I'm looking at the numerator. If I plug in 2 for my x, that's going to be negative. Same if I plug in positive 2. If I plug in 0 for my x, that's going to be positive. This is negative. This is positive. This is negative. This is decreasing, decreasing, increasing. So it looks like this guy here is a max, min. This guy here is a max, because they're in the domain and you're decreasing and then increasing, then decreasing. So this is going to be minus 1 comma. I'm going to plug that into the original graph. So that's going to be minus 2 and 1 comma 2 looks like, because it's going to be 4 divided by 2, and then it's going to be minus 4 divided by 2. Right, so now I can do the increasing, decreasing, max, min. We're increasing from minus 1 to 1. We're decreasing from minus infinity to minus 1, and from 1 to infinity. I have a maximum at 1 comma 2. I have a minimum at minus 1 comma minus 2. That's step 4. Move on to step 5. We're going to do concave up, concave down, reflections. Here we're going to use the second derivative. So we're going to have the critical points. This is going to be x equals 0 or x equals plus or minus rad 3. Plug in some random numbers like 2 is over here, minus 1 is over here, 1 is over here, 2 is over here. So if I look at the numerator, plug in negative 2, I would get a negative times a positive in the top over positive. The denominator is always positive, in fact. This here is a negative. If I plug in -1, I would get a negative times a negative. It's positive. If I plug in a +1, I would get a positive times a negative. It's a negative. If I plug in a +2, I would get a positive times a positive. It's a positive. So this means I'm concave down, concave up, concave down, concave up. And these guys are all inflections. So this means 0, 0 is an inflection, a minus rad 3, comma whatever, positive rad 3, comma whatever. The function was x squared over x squared, 4x over x squared plus 1. So with rad 3, I'd have 4 rad 3 over 4. It's just rad 3. And if I had minus rad 3, so we have that. So now I can summarize concave up, concave down, inflections. So concave up from minus rad 3 to 0, from rad 3 to infinity. Concave down from minus infinity to minus rad 3, and from 0 to rad 3. Inflection points, minus rad 3, minus rad 3, 0, 0, rad 3, rad 3. Now with all that, I'm reaching to step 6. I'm going to sketch the graph. So I'm going to put in the intercepts. 0, 0. Horizontal asymptote is 0. That's just that. Horizontal asymptote. What are the, do we have any other coordinates? Yeah, we had max at 1, 2. And we had a min at -1, -2. We had inflection points that are going to occur. Here is an inflection. Over here is an inflection. And over here is an inflection. Now let's do the intervals, increasing between -1 and 1. Of course, we're decreasing otherwise. Concavity. concave up, between here, and here, concave down elsewhere, and with that I can now draw the graph. So I should be decreasing. I know I have a horizontal asymptote, concave down, which means I should look like down like a frown. Here I'm up like a cup, still up like a cup, but increasing. Down like a frown, but increasing. Down like a frown, but decreasing. Up like a cup, but decreasing. So that would be your graph. That was about 10 minutes. Yeah, which is a difficult problem. As you can probably see, it was much harder than the last problem that we did. Because all these weird numbers like radical 3 and all sorts of stuff. And it should look symmetrical, like the left and right side is like a mirror image of the other one, but whatever. I'm not gonna, this is good enough to get like full credit. Like I can clearly see how things are curved. You're shaped like a smiley face or a frowny face when you should. And you're increasing when you should, you're decreasing when you should be. You create the intercepts that you should be creating. You switch from, you have the right inflection points, the right maxes and mins. That's an okay graph. Yeah, you want to get to the point where you can just keep going, and you never really have to stop to think about it, what you're doing, because these problems are long already. You don't want to make it longer. So there's the whole thing. You don't want to make it longer by like, wait, what am I supposed to be doing again? Like it's gonna mess up. It's gonna mess you up. You're gonna run out of time. I definitely don't want to do start another topic. So let me finish this example. So hope it's not an annoying one. Okay, so trigger the coffee. All right, example C. So one, we're going to find a domain. Can be anything except one. Two, we're going to find the intercepts. So x-intercepts, this is your x is going to be plus or minus 3. Y-intercept, plug in x equals 0, you're going to get minus 9. Three asymptotes. Let's look at the horizontal asymptotes. It's going to be 1. I should show what that is. This is by ratio of the leading coefficients. Vertical asymptotes. x equals 1. Denominator equals 0 here. Moving on to step 4. Where are we increasing, decreasing? Where do we have maximums? Where do we have minimums? So to do this one, we're going to need to do the first derivative test, which means we care about this guy. We're going to have our critical points. For the derivative to be 0, you need x equals 9. For the derivative to be undefined, you need x equals 1. Plus that in the first derivative. Pick a random number, 0, 2, 10. So if I plug into the first derivative 0 for x, I would get a negative. So I would get a positive number on top. I would get a -1 on the bottom. If I plug in 2 for x, I would get a positive number on top. I would get a positive number on the bottom. If I plug in 10 for x, I would get a negative number on top, get a positive number on the bottom. So here this is negative, which means decreasing. Here this is positive, which means increasing. And here this is negative, which means decreasing. Now, 1 is not in the domain, so that's nothing, but 9 is in the domain, so that's a max. So we'll notice that your y would be equal to 9 squared minus 9 over 9 minus 1 squared. So that's 9 times 9 minus 1, or 9 minus 1 squared. That would cancel into that. So you get 9/8, looks like. So this is 9, 9/8. So here we're going to look at increasing, decreasing, maximum, minimum. There is no minimum. The maximum is at 9, 9/8. We are decreasing from negative infinity to 1, and from 9 to infinity. We're increasing from 1 to 9. Move on to step 5. We're going to do concavity, concave up, concave down, inflection. Which means we're going to look at this guy. Critical points. X equals 13, x equals 1. 13 is where it's 0, 1 is where it's undefined. Going to plug into the second derivative. So remember, I can't touch 1 because it's not in the domain. But I'm going to try 0, try 2, try 14. So plugging into the second derivative, if I plug in 0, I would have a negative on top. The bottom is always positive because fourth. This is negative, it's concave down. If I plug in 2, it's a negative. Still concave down. If I plug in 14, that's positive. It's positive, concave up. That means that this guy here is an inflection. And that would be 13 squared minus 9 over 13 minus 1 squared. Oh, that's going to be ugly. This is 169 minus 9, 12 squared. 160 over 144. Which seems to be like slightly bigger than 1. So concave up, concave down, inflections. This is step 6 where we're going to graph it. Okay, let's go back. Where are we? Intercepts plus or minus 3 and y equals 9. So minus 3 plus 3, y equals minus 9. Asymptotes, horizontal, y equals 1, vertical, x equals 1. So and okay, so those are the asymptotes in. Maximum 9, common 9 over 8. It's going to be slightly higher than 1. Minimums, none. Inflection point 13, comma 160 over 4, which, okay, let me move this. I think I see what this graph is doing. Do this 160 over 144. It's going to be over here. It's going to be at 13. Let's put in the intercepts. We're increasing between 1 and 9, decreasing everywhere else. All right, so 1 and 9, we're increasing, decreasing otherwise. Okay, concavity. From 13 to infinity, we're concave up. And we're concave down pretty much everywhere else, it looks like. We stop at 1. Ugh. Yeah, that's, I think we put in everything. So let's draw the graph now. I should be decreasing concave down, so decreasing like a frowny face, passing through these guys. and then that. And then here, increasing concave down until I hit that part going through 3. And I'm going to turn her. Turn around here, and go to a frowny face, and then head off like that. So that's that graph. Yeah, and that's it. That's what that graph would look like. Okay, so I would say for so that's all I want to show you with curve sketching, because those are the kinds of problems that I'm going to ask you. And that's that. The topic we will do for next time, which is actually the last topic in the derivative section, is another word problem type called optimization, which there's a handout for on the class webpage, and I'm going to paste it here. So it's another word problem, 6-step process once again. So I'd recommend you read up on it, maybe even try a couple problems if you think you can. Yeah. So it's another word problem section, but it's going to be, again, it's also 6 steps. So you can read through those, maybe even take a crack of it. Problem 1 should be something that you can kind of struggle through, I think. And, you know, with the summer moving so fast, it'll be good if you actually tried it something before class. And so you can follow during class a little bit easier, especially since we have 3-hour class. It's not easy to stay focused. It helps if you kind of look at things ahead of time. But yeah, we will stop there. So yeah, optimization, last topic in the differential calculus part of this course. Which is all I have for you tonight. So it's already late, so I'm going to let you guys go. And yeah, so remember to look over your tests and submit regrade requests. I'm probably going to accept those until the end of this week, just before your test 2 starts. So maybe Thursday or Friday. And like I said, I'm thinking of doing test 2 say Saturday morning until Sunday at 6 or something like that, as opposed to the Friday. Give you a little bit more time to study. But yeah, have any questions, let me know, email me. I know some people are asking me about the homework. I will get the rest of that to you. And I think that's it for now. So good night. Have a good night, everyone. And I will see you guys tomorrow in the next one. Ciao.